Okay, we're going to get started now. We're on chapter 6 now. We're going to talk about force and motion. Let's see what are things you have to do for science. Okay, we're going to do force and motion. We're going to read about force and motion. Everyone on page 150? Yep.
I'm there.
After secret.
All right, let's get started. Okay, force and motion. Think for a moment about what the world would be like without engines. Rockets and railway locomotives, airplanes and automobiles, army tanks and farm tractors, dune buggies and bulldozers, motorcycles and semi-trailer trucks, ocean liners and oil tankers, helicopters, go-karts, and space shuttles. These are just a few of the devices that would not be able to operate. To go from place to place, you would have to walk, run, pedal a bicycle, or ride a horse. Long journeys might take weeks, months, or even years. On the water, men would be able to travel only by swimming or by rowing themselves in boats. Flight would be limited to drifting about in hot air balloons, and space exploration would be impossible. Factories and mills could not produce clothing, furniture, paper, appliances, and electronic devices. Power plants would close down, cutting off electricity to heaters, lights, refrigerators, air conditioners, hot water tanks in our homes. Without engines, our day-to-day lives would be much different than they are now. So we all need engines. Your car has an engine. A lot of power plants have engines to keep electricity. We're going to understand what an engine is. An engine is a device that converts energy from a natural source into useful work. All engines are excellent workers. They do jobs for man that he cannot do well or even at all by himself. Engines are best at making objects move. In this chapter, we will investigate how a number of different engines operate. The first step in understanding engines is to understand where motion comes from. Forces necessary for motion. Have you ever stubbed your toe on a heavy piece of furniture? Have you ever done that? You know what stub your toe means?
What, mister?
Stubbed your toe, you know what stubbed your toe means?
No.
Like you're walking and you kick the table with your foot.
The little finger.
A little toe, yeah, that means toe.
That happened me for each day 1,326 times a day.
All right, so have you ever stubbed your toe on a heavy piece of furniture, or felt a cool breeze on a warm day, or fallen down a flight of stairs, or licked a triple dip ice cream cone? All right, if you have, then you have sensed forces acting upon your body. Although you may not realize it, you must use forces every day, whether it be to kick a soccer ball, climb a tree, to open a door, or to write a letter. Without forces, your lungs cannot take in air and your blood cannot flow. Forces are important in our world because we need them to produce motion. Forces themselves are invisible. They cannot be smelled or tasted. Forces can only be felt. Imagine that you are diving off a diving board. When you push against the board with your feet, you feel the force of the board spring pushing you back up into the air. Have you ever jumped on a trampoline? Yeah? You know where you go.
Yes. Yes.
That force is pushing you back up. So you put force in it, but then the force is pushing you back up. It is not long, though, until you begin to feel the gravity of the force of gravity pulling you down to the water. Then splash. You feel the force of the water pushing against your body as you slice through it. All the forces in this example cause motion either by pushing or pulling an object. A force, then, is best described as a push or pull. So force is push or pull. Force of gravity. Gravity is the force that holds the galaxies and solar systems of our universe together. It keeps the Earth in its orbit around the sun and the moon in its orbit around the Earth. Without gravity, everything on Earth that is not fastened down, air, rocks, oceans, cars, animals, and people would float away into outer space. All right. Gravity prevents your food from rising off your plate. It pulls a baseball back down after it has been lofted high into the air. It causes you to fall when you trip on the tree root. and it keeps you from bumping your head on the ceiling with every step you take. Of all the forces, gravity is actually the weakest. Gravity is the force of attraction that exists between any pairs of objects. And so we have gravity. This is gravity. Okay? That's gravity. Everything goes down. So the man who discovered gravity was sitting under an apple tree, and then an apple fell on his head. And that's what he started thinking about. Why did that do that? So he was going, and he realized gravity. And something has to pull it down. You may remember that matter is anything that takes up space and has mass. The strength of the gravitational force between two objects is determined by the mass, or the amount of matter, of the objects that the distance between them, and the distance between them. Small objects, such as your pen and this book, or this book and the desk, or your house and the house next door, pull on each other with an amount of force too small to be noticed or measured. But very large objects, such as the Earth, of a strong force of gravity. Weight is the measure of gravitational force, or the downward pull existing between the Earth and the particular object. So basically, your weight is how much your mass is, how big you are, and how dense it is. And then you put the scale in between the Earth and you push down on it. The gravity pulling you down. So that's how you figure out how much you weigh. It all depends on the gravity that's being pulled, the downward pull that's pulling you to Earth. So I explained that really bad. Okay, gravity is the force of attraction that exists between any pair of objects, but the strongest gravity is the Earth. What the Earth will do. The Earth will pull. That's why we're able to sit, stand, lay down on the Earth, because it pulls us down to the ground. And so what you do is you put a scale in between you and the Earth, and however strong the pull is, depending on how big you are, how much you weigh, well, that's going to be how much you weigh. So a car is going to weigh more than this pencil because it's bigger than this pencil. And so the Earth is pulling down harder on this because on the car, because there's more to the car. It's a bigger mass, whereas in this is smaller, so it's easy to handle. So as you get bigger, you're going to weigh more because you're going to have more mass, the amount of matter. And you guys will learn more about matter and mass as you go on in the following grades. Okay? We're going to talk about force of contact. Ready? You place your hand palm down on your desk and push. You are applying a force to the desktop. You would be using a contact force, a force that occurs when one object pushes against another object. So right here, see this wall? I'm pushing up against it. Okay, that's contact force, a force that occurs when the object pushes against another object. So you have a table, push on the table. Push down on the table. That is called force or contact force. So that's one type of force. Your chair pushes against you with a contact force to keep you from being pulled to the ground by the Earth's gravity. In a game of football, someone on the opposite team might use a strong contact force to tackle you. If you were to stand outside in a hurricane, the wind would push against you with a force of contact powerful enough to blow you over. Ringing a doorbell, dribbling a basketball, playing the piano, hitting a baseball with a bat, and pushing a lawnmower are some ways in which you might use a contact force in everyday life. So that's some ways you use a contact force. Playing soccer, pushing your door, stuff like that. All right, let's read Private Investigator. Gravity on the moon. Because the moon is much smaller than the Earth, its force of gravity is weaker than the Earth's gravity. This means that an object would weigh much less on the moon than it would on Earth. On Earth, the weight of an astronaut's body added to the weight of his spacesuit might be over 300 pounds. But on the moon, he would weigh only a total of 50 or 60 pounds. To calculate how much you would weigh on the moon, weigh yourself to find out your exact weight. Then divide the number of pounds by 6 to define what your moon weight would be. Can you calculate how much your total weight would be on the moon if you're wearing a 150-pound spacesuit? All right, let's do that. John Carlos, how much do you weigh?
Like 100, a little like that.
100 pounds. Okay, let's do 100. 100. You would weigh 16 pounds on the moon. If you had a spacesuit on as well, you would weigh 41 pounds. Who else wants to know how much they would weigh on the moon?
How many, mister?
You would weigh 16 pounds.
16. I listen 6.
Monse, how much do you weigh? Nothing. Gloria, do you know how much you weigh?
I don't know if I am 100. I don't know, mister. But I think I am 100.
All right, well,
Little like
next time
that.
you weigh yourself,
I weigh 63.
you weigh 63, you would weigh 10 pounds.
I think I don't weigh like that. I don't know.
I don't think you weigh that either. So 150 plus 63 divided by 6. With a spacesuit on, Lizzie, you would weigh 35 and a half. Very light. Okay, force of friction. Let's read about friction. If you were to punch hard until you were swinging really high on a swing and then were to stop pumping, what would happen? You would gradually begin to slow down and swing slower, lower and lower until you're no longer swinging at all. The same idea is true of a ball. You may kick it hard, but sooner or later it will still stop. The toboggan slides easily down the side of a covered hill, but quickly loses speed when it reaches the bottom. If you have ever ridden a bicycle, you know from experience that you cannot coast forever without pedaling, which means to ride without pedaling. In all 4 of these examples, a force causes a moving object to stop. This force that resists motion is called friction. Friction is a special type of contact force brought about when the surfaces of 2 objects rub together. Even though a surface may look smooth to you, it is actually made up of millions of microscopic bumps and cracks. When one surface is moved over another, the uneven edges of the 2 surfaces catch on each other and resist the sliding motion. Not only does this friction resist motion, but it also causes the 2 surfaces to wear down. So you do not want to wait for the swing to slow down on its own. To reduce your speed very quickly, you might drag your feet, rubbing the bumpy surfaces of your shoe bottoms against the rough dirt. But if you did this often enough, you would wear holes in the bottoms of your shoes. There is no such thing as friction. Every surface would be more slippery than the smoothest ice. You would not even be able to walk around. Cars would not be driven from place to place. Pens and pencils could not write. Nails would fall out of the walls and ceilings, causing buildings to collapse. We'd be thankful that I created with the force of friction. Okay. Friction makes things stick, makes things not move. So friction is what causes our cars to drive. And so the 2,
Like,
well,
it's like a rock.
kind of like a rock, it rubs together. And so if it rubs together, it's not gonna move. For example, listen, I don't know if you can hear it, but take your pencil and put it on your book and rub it on your book like this. Can you hear that sound? Do you hear a sound?
Yes.
That's friction. So if I toss it like this, watch what happens. Ooh. See how it stops? I'm throwing it so it moves, except for I tilted it so you guys could see it. All right. Now if I have it like this, see how it stops?
Yeah, that is stop. Look.
All right, that's friction. It's because the hard surfaces, very small, called microscopic, on the pencil and the microscopic parts on the paper are not even. They're not smooth. They're not flat. So they crash together and then they stop. That's friction. Okay. So this is the comp check that you guys have to read.
3.1.
Yeah.
That is our homework.
Yeah, that's one of them. We're gonna keep reading. Now we're gonna talk about electricity and magnetism. Okay.
Where, mister? Oh yeah, I already found it.
All right. You have probably noticed that when clothes are taken out of the dryer, they have a tendency to stick together. Have you ever done that? Does anyone have a dryer at their house?
A what?
A dryer?
What does that mean?
You don't know what a dryer is?
Nope.
Oh,
Secadora.
oh yeah.
Does anyone have one at their house?
Yes.
Yes.
Have you ever
Already
taken it
know
out
it.
and there we go. Have you ever taken your clothes out and they stick together?
Oh, yes.
Yeah.
Yes.
So that's what he's talking about here. The static, the cling occurs when electrically charged pieces of clothing are pulled together by electric forces between them. An electric force causes electrically charged objects either to attract or to repel each other. Why isn't my mouse working? Okay. Electric charges are positive or negative. If two objects with the same charge, both positive or both negative, are brought close together, they will repel each other. So if they have a positive charge with a positive charge, it's gonna push apart. But if two objects with different charges are brought near each other, they will attract. A simple rule to remember is that like charges repel, opposite charges attract. So the same charges will push away from each other, but different ones will attract each other. For instance, fluffy kinds of clothes tend to pick up a positive charge in the dryer, while smooth fabrics pick up a negative charge. Since two fluffy socks would both have a positive charge, they would repel each other if you brought them close together. But a fluffy sock would stick together. But a fluffy sock and a smooth shirt would stick together. Electric forces tend to develop many of the conveniences we often take for granted in modern life. Refrigerators, air conditioners, light bulbs, stereos, digital watches, computers, telephones, all electrical devices depend on electric forces to operate. Okay? All right, so on the bottom of page 154, that's your project you have to do this week, okay? Good. You have a week to do it. All right. Yeah.
We need to put like that. The
Right.
first one is easy, but the second one, how we can do that, bro?
If you have a balloon, do that.
I don't have.
We'll see if you can get one.
Oh, mister.
Okay. Okay. Force of magnetism. If you were lost in the woods, or on page 155, if you were lost in the woods, you would use a compass to determine which direction is north, so that you would find your way again. The first compasses were made of a, you guys know what a compass is? Do you know what a compass is?
Compass means.
This is a compass right here.
Yeah.
See how it moves?
It's like this one, look.
Yeah. So it shows you where's north. So right now I'm facing north. That would be west, and that would be east, and then behind me would be south. Yeah. Okay. The first compasses were made of a special kind of rock known. Men dug these rocks out of the ground and called them lodestones, pieces of naturally magnetized iron ore. They discovered that when a lodestone was allowed to swing freely, one particular end always pointed north and the other always pointed south. Each magnet, such as a lodestone, has a north-seeking pole, usually called the North Pole, and a south-seeking pole, or the South Pole. Take two magnets and touch them together. If they jump apart, it is because you touched like poles, two north or two south, and they repel each other. Have you ever had two magnets and you try to push them together and they go like this?
Yes.
That's because they have the same. Remember how we said positive and positive don't attract? Positive and negative attract? It's the same thing with the magnets. North and north, you can't get them to connect, no matter how hard you try. But north and south connect. But if they pull firmly together, it is because you brought two opposite poles. So north and south connect, like you see in those photos. The north pole of one and the south pole of the other into contact. We see that the rule for magnetic forces is very much like the rule for electric forces. Like poles repel, which means they don't connect, but opposite poles attract. They do connect. Magnetic forces will also attract certain types of metal, such as iron. Even a very small magnet can pick up tacks or paper clips. Cranes in junkyards have huge magnets attached to them for picking up and moving heavy loads of scrap metal. Magnets also have many uses around the house. Any device with an electric motor, such as a ceiling fan, a garbage disposal, or a clock, has magnets in it. Telephones, headphones, and loudspeakers contain magnets. Magnetic strip holds the doors of your refrigerator and the freezers closed. And you may have decorative magnets stuck to the outside of these appliances. Who has a magnet on the refrigerator?
You want to show it to you?
Yeah, if you have one,
I have a lot.
if you have one, go get it. If you have two.
What, mister?
Wait, I also will get one. Wait, I'm coming.
If you have two, get two. All right. Do you have two?
What, mister?
Do you have two?
Yes.
Go get another one.
I have two, mister.
Go get it.
I have 1, 2, 3, 4. I don't know how many I have. I get it.
Yeah, get them.
Mister, these are two that are there. This
Uh-huh.
and this.
All right. Try to put them together. See what happens.
They put.
All right. Now flip one side.
How?
No, there's. They
How?
two.
What?
You look. First look.
How?
That page
Mister,
that
the
you look.
mine no look.
Now
But
I do to our side. They
How?
connect.
You're weird. All right. Let's look at Lizzie's. Lizzie, let's see yours.
look, mister, they are in the black side and look now. They don't paste.
The
But here, yes.
the tools of my mother. The shoes.
Look, 2 more.
See how? All right. Everyone watch Lizzie's.
I will put it there one more time.
Do the two blue sides together.
Huh?
Lizzie, try to put the two blue sides together. All right, that's the two. Okay, now put the blue sides together like that.
They don't paste.
They don't connect. They're repelling each other. Yeah, you can put them together, but they don't connect automatically, okay? Okay.
Mister, because look mine is there. Look. You do like that first and they connect. Look them. They connect and then you take it out. And you say that we put it like that, right? Like that.
Yeah, and it connects, right?
Like that. Look and they connect.
Now put white side with white side.
No, that I cannot.
Right.
Look.
Mister.
Yep.
The massive one.
It's a huge one. Okay, we're gonna keep reading because we need to finish this.
I will put it.
Mister, the comprehension check 6.2 is hunger, right?
You're not gonna like me after the end of this class, but okay. All right, we're gonna.
I'm coming, Mister. I will leave deep.
Okay.
They paste, mister.
Yep, I can see. Okay, let's keep reading. Magnetic forces will also attract certain types of metals such as iron. That's how we already read that. Telephones, headphones, and loudspeakers contain magnets. A magnetic strip holds the doors of your refrigerator and freezer closed. You may have decorative magnets stuck to the outside of your appliances, like the fridges, like the ones you guys had showed. Probably the most important use of the magnet, though, is as a compass. Without his compass, Christopher Columbus would not have been able to discover America in 1492. All right, so comp check 6.2. Okay. All right, let's go to 6.3.
Homework, right? Homework.
Yep, homework.
For 6.1,
Is there how many comprehension
for
you will
6.1 to 6.3.
6.1 to 6.3. We're going to keep reading 6.3 right now.
All the 2 pages, mister.
Uh-huh. Oh, no, 3. 6.1, 2, 3. Okay.
Okay.
All right. Let's keep reading. It says work and energy. Work, work, and more work. Did you know that when you are playing hard and having a good time, you are actually working? Riding a bicycle, throwing a football, or swimming across a pool may be fun, but each of these activities is a form of work. Scientists say that work is the result of a force moving an object. So work is the result of a force moving an object. Whether you are hammering a nail, sawing a board, setting the table, washing the dishes, biting an apple, jumping rope, you are applying force, moving an object, and performing work. If, however, you just merely apply force and push every hard on a wall, no work would be done because the force you're applying would not be moving anything. So look at this wall right here. I'm pushing up against it and it's not moving. So it is not work. But I have my phone in my hand. That's work, okay? Because it is moving. Energy, the ability to do work. Forms of energy. All work involves the use of energy. So everyone that moves uses energy. In fact, scientists define energy as the ability to do work. No one knows what energy really is in itself. So scientists define it by what it does. Work. Energy can appear in many different forms. There's light. Without light energy, you cannot see at all. The sun radiates light energy upon the earth. At night, we fill our homes with light energy by turning on light bulbs. So you see the light energy behind me right here? This right here?
Yeah.
That's light energy from the sun. You see this? That's light energy from electricity, from a light bulb. Heat energy we can feel. An oven or a burner on a stove gives off heat energy. Warm clothes help to hold in your body's natural heat energy on a very cold day. Now we have atomic energy. Atomic energy is released when atoms are either split or joined together. A nuclear power plant uses atomic energy to produce electricity. Another form of energy, which is chemical energy, is stored in the bonds that hold molecules and chemical compounds together. And electrical energy is found in such things as lightning bolts and the power lines that bring electricity to your home. Types of energy, okay? Most energy belongs into 2 basic types, kinetic and potential. Kinetic energy is the energy of motion. So if it's moving, it is kinetic energy. A flying bullet, a speeding train, a falling rock, a bouncing ball, a running boy, and a shooting star all have kinetic energy because they are moving. Man, I wish we were in class because I had a game that we used to do. Actually, let's play the game. We're going to play that game afterwards. I'll show you what it is. All right. What happens when a bowling ball rumbles down the alley and strikes the pins? They
What
fly
happened?
everywhere, which went with a loud crash. So have you ever played bowling?
One?
Bowling? Do you know what bowling is?
Yes.
Right here. Have you ever done
Yeah,
that?
yeah, yeah.
So
Yes.
kinetic energy gives the bowling ball the ability to work. So the ball that's moving is kinetic energy. In this case, putting the pins into motion. Each moving pin also has kinetic energy and has the ability to do work by causing other pins to move. Even on the best of throws, a bowling ball does not hit all the pins. Instead, it knocks over some pins, which then hit other pins, which bump into still other pins until all 10 have fallen down. So that's kinetic energy, the energy of motion. So if it's moving, it's kinetic. This right here, a book dropping, kinetic. The other type of energy is potential energy or stored energy. When released, stored energy becomes the energy of motion. An object with potential energy has potential energy because of its position. It is exposed to a force. A book on a bookshelf is being pulled down by gravity but does not move. It has potential energy. If the book is pushed off the shelf, the book's potential energy changes into kinetic energy as it falls to the ground. Another object with potential energy is an inflated balloon. The energy you use to blow up the balloon is stored in the balloon as potential energy. If you do not tie the balloon, you must hold the stem to keep the air from escaping. As long as you hold the balloon in your hand, the balloon will not move on its own, even though the air outside is pressing outward with a force of contact. But if you let go, the air will escape. The balloon's potential energy will be changed into kinetic energy as it flies across the air. Who's ever played with a balloon?
Play with a balloon.
Yeah, until you blew it up and it was full, and then all of a sudden you let it go and it went away.
Yes.
So potential energy is when you blow it up, you hold on to it. Potential means it has the potential to move. It might move. It could move. And if I let it go, all the energy that's inside will move. The kinetic energy is if I let it go and then it does that. That would be kinetic energy. Okay. Potential is when it's not moving. Kinetic is when it is moving. All right. Let's play a quick game. Yeah. You want to play a quick game? All right. Everyone needs to stand up. Okay. So you have to put your cameras on. I have to see you. All
We
right.
just end up.
Yeah, I'm gonna show you this game. All right. This is the game. Okay. Here's what we're gonna do. We have two types of energies: potential and kinetic. All right. Which one is motion? Which one talks about moving? Which one is the energy of motion? Potential or kinetic?
Motion.
Which one? There's two. Potential and kinetic. Which one talks about
Kinetic. Kinetic.
kinetic? Very good. So kinetic is moving. So when I say kinetic, you have to move. You have to do something. Okay?
Okay.
And when I say potential, you have to stop. Okay?
Okay.
Sound good?
Okay.
Okay. So when I say potential, you stop. When I say kinetic, you move. And if you move, you're out. So if I say potential and you start moving, you're out. Okay? All right, are you ready? Kinetic. Potential. Potential. Ah! Kinetic.
I'm out.
Potential.
I am out. Right, mister.
Kinetic. Yeah. Kinetic. No, why'd you guys stop? All right, let's see. Carlos, you're in. Let's see if you can do it one more time.
Okay.
All right, I'm going to try to trick you guys, all right? Don't follow what I do, follow what I say, so be listening, okay?
Mister, because I confused with the words.
Okay, kinetic means you move. Potential means you stop.
Okay. Potential, stop. In kinetic.
Move. Yeah. All right, ready? Kinetic.
Okay.
Potential. 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 Ah! Kinetic. Potential. Kinetic. Kinetic. Very good. Good job, guys. Okay, let's finish this chapter, okay?
Okay. Ugh.
All right. You guys tired now?
Nah.
No.
You guys have PE today?
Yes.
What?
You have PE today?
Yesterday.
No.
Oh,
Yesterday one.
Okay, we had a little PE class in science class. Okay, we're at that very last paragraph where it says one special form of potential energy. One special form of potential energy, chemical energy, is found in such items as a piece of wood, a lump of coal, a gallon of gasoline, and a slice of apple pie. The energy stored up in these things is released as heat energy through burning or some other chemical process. So if it burns, like wood, apote, stuff like that, it has chemical energy. It'll release heat if it's burned. Now let's talk about transfers of energy. A transfer of energy occurs when one object gives some or all its energy to another object. So that's a transfer. So if it gives one to the other, it's a transfer. An example of the bowling ball, some of the ball's energy is transferred into the pins when it strikes them. So when you roll the bowling ball and it hits the pins, that is a transfer of energy. The ball slows down after hitting the pins because it has less energy. Some has been given away. The kinetic energy of the ball is transferred as kinetic energy to the pins. We can see that the pins have kinetic energy because they move. Remember, kinetic means they move. There is no change in the form of the energy. Sometimes, however, energy does change form when passed from one object to another. We have already talked about a book falling off a shelf. So remember, if you want to put the book back on the shelf, you need to make a use of two different energy changes. First, chemical energy that is stored in food as potential energy is released in your body and changed by your muscles into the kinetic energy you're moving. So who had breakfast this morning?
Breakfast.
Raise your hand if you had breakfast. Okay, that is chemical energy because right now you're moving and all that stuff. So that transferred into what you need for your muscles to move. And then say you had to put a book back on the bookshelf. That would be your kinetic energy. So kinetic energy is the moving. So chemical energy that is stored in your body as potential energy is released into your body. So it's giving you the nutrients and everything so you can move and stuff like that. And then it is kinetic energy. All right. As your arm lifts the book, it transfers its kinetic energy to the book where the energy is stored as potential energy. The book on the shelf has potential energy because it has the potential to fall to the ground. For example, I have this right here. It has potential energy because it can fall to the ground if I move it. So if I go like this, it falls. So potential energy, kinetic energy. Okay? Transfers of energy happen all around us all the time. No food can be grown or cooked or eaten without the transfer of energy. The wheat and the corn in the fields and the fruits and vegetables in our gardens ripen when plants change light energy from the sun into chemical energy by means of photosynthesis. No clothes can be made on, put on, or washed, or worn, or torn, or altered, or repaired. No dog can bark, no bird can fly, no bell can ring, no breeze can blow without transfers of energy. Work from muscles. For hundreds and hundreds of years, man had only a few simple machines such as wheels and levers. He had to depend largely on his own muscle, on his animals to provide the energy for doing work. Human or animal muscles pulled plows, hauled water, and dragged heavy loads. It was slow, exhausting work for man and his animals. Today, much of the world's work is done with the muscle power. In places where muscles supply most of the energy, people spend most of their time trying to get enough to eat to stay alive. Men and women and children must work from sunrise to sunset, day in and day out. There is no time for little else besides hard, heavy work. All right, we're going to finish this last section, energy from muscles, and then we will be done for today. All right, muscles get their energy from food and oxygen, which are brought to them by the blood. Each muscle is a tiny chemical plant, an energy powerhouse in which the potential energy stored in food molecules is released using oxygen in a process much like the burning of fuel. Every movement that a person makes is made with muscles. Running, walking, lifting, pushing, pulling, talking, even the beating of the heart as it pumps blood throughout the body each moment. All these depend on the energy of muscles. Doing heavy work with muscles is tiring because it requires a person to use up much of its body's stored energy. From the beginning, when God created man and gave him the task of subduing the earth and ruling over its creatures, man has sought other sources of energy and easier ways of doing things. His search became especially necessary after man fell into sin and God cursed the ground because of his sin. Man now had to earn his living in the sweat of his face. The history of technology has been largely the story of man's search for devices that can make his life and work on earth less difficult. Such devices that can convert energy from natural sources into useful work are called engines, all right? That's an engine. We've been looking for an engine to make things easier for us, okay? So in the comp check, you have to define energy, kinetic energy, potential energy, engine, transfer of energy, and work. Then, is it accomplished if you push hard on a wall? Why or why not? And name an item in which chemical energy is found. Those are pretty easy, okay? And that is all we have for today.
We have 3